odd and even functions, right? Odd and even are words which describe kinds of symmetry. Kinds of symmetry. And the reason why I'm coming up with them now is because, as you've noticed, when we graphed all of the trig functions, they all exhibit various kinds of symmetry, sometimes multiple kinds. Okay? So, before I get to this, let me just give you the classic example of odd and even functions, and then we'll fit our understanding of trig into it. Okay? So, draw with me a small set of axes, actually two of them. Two small sets of axes. Right? These don't have to be huge or beautiful, just enough to see some bare geometric features. Okay? So, we're going to very quickly draw two kinds of functions with two kinds of symmetry. Okay? So we're going to do y equals x squared, and we're going to do y equals x cubed. These are very, very easy, but you'll see why I've chosen these in a second. Okay? Y equals x squared, we know what this looks like, right? Y equals x squared. It's a familiar parabola, okay? Now, in order to understand what's happening here with the symmetry, I'm going to phrase this a little bit differently. I've said y equals x squared and y equals x cubed because that's how we're used to hearing it, okay? But a more technical way of saying these things, just slightly more technical, is to say, instead of y, to say f of x. Now, this is not the first time you've seen it, but in case it's been a little while, f just stands for function, right? And it means that over here is something that you put x into. It's a function of x. Okay? You can have functions of anything. Functions of time, functions of speed, functions of position, displacement, and on and on and on. I put x into there, so it's a function of x. This is also a function of x. I could call them different things, but it doesn't matter. Okay? Now, you can see that this thing is symmetrical, right? So for instance, if I took a value like x equals 2, and I draw that up to a certain value, you'd get 4. Right? And if I go to the opposite side of the y-axis, and I go to minus 2, and I draw my point up, I will get the same value, right? So the way of saying that with this language is to say that f of 2, right, my x value is 2, so that's why it appears where the x is equal to f of minus 2, okay? And actually, I can take this for any value of x on this particular function because it's symmetrical all the way. It's not like it gets to, 1,000,005 and then decides, stuff that, I don't want to be symmetrical anymore. All values of x, right? It's going to do that. So I can state this generally. I don't just have to put particular values. I can say f of x equals f of minus x for any value of x, right? That's what gives this what we call, well, this is reflectional symmetry, isn't it? It's symmetrical about the y-axis, okay? And we call this even symmetry. In a second, I'll ask you why. Let's come over to this guy, right? In fact, I think you just drew one of these, didn't you? Yeah? So what you've got is this. You've got this shape in here. It levels out and it's flat right there, unlike tan, which blows through the axis at a gradient. This blows through at 0, okay? Now, there's still symmetry here. There's still symmetry here, but it's not the same kind, okay? For instance, if I take the same value, 2, okay? And you go up to the corresponding value up here, right? It's going to be 2 cubed, which is 8. Now, when I take the same value on the other side, and I go to minus 1, minus 2, okay? Well, unlike here, I'm not going up to the same value, 8, clearly. Right? But what I am going to is the same value, but negative, right? Because minus 2 all cubed, of course, is minus 8. Okay, so how would I say this? Look at that statement we made over on the left, right? Yeah, go ahead.
F of negative x is equal to negative f.
Okay, I'm going to come to that in a second. I just want a statement from these numbers, right? F of 2 is 8. We'll get to the generalization in a second. And that's equal to minus f of minus 2. Okay, now, excuse me, you can see this minus sign. I could kick him over here if I wanted. I can multiply both sides by minus 1. It's the same statement, like so, okay? Because f of 2 is 8, so this would be minus 8, which is, of course, the same as f of minus 2, minus 8. So now if I state this generally, I generally do it the other way around. I would say f of minus x is equal to minus f of x. Okay? So what I've got here is not reflectional symmetry, right? It's not reflecting across there. It's not even reflecting across here, okay? In fact, what I've got is rotational symmetry around the origin. Can you see that? If I were to take this part up here in the first quadrant and then just turn it around, you'd get this down here in the third quadrant, okay? So here, reflectional. Okay, and we call that even symmetry, or it's an even function. And over here, we have rotational symmetry. And we call that odd. Okay, now there are a variety of reasons why they are called odd and even symmetry, but I said I would ask you a second ago why you think they're called odd and even. There's one reason which just jumps out at you, which I've picked these two examples specifically for this. Yeah?
To use an even number versus odd number.
Thank you. So you're like, even? Odd. Now ordinarily I would frown on thinking, oh look, I found one example and another, that's it, that's enough to generalize the pattern. But you might be starting to think, hold on a second. I said this was x squared, right? But on a different scale, this would be x to the 4, right? I just have to stretch things out this way. Or x to the 6, or x to the 8, or x 1024, right? They're all actually going to look pretty much like that, just steeper. And so they're all going to exhibit the same symmetry because they have even powers. You can make the same argument over here. Right? If this is x to the 5, x to the 7, 9, 1023, they're all odd degrees, right? So therefore you're going to get odd symmetry. Now, there's the idea. There's the idea.